Today I'm going to go over Simulink, Matlab, whatever simulation stuff for BAJA suspension kinematic and dynamic analysis. So you already probably have Matlab, if not downloaded. And downloading Simulink and Simscape, I'll attach this document and you can just read through this and go through it step by step. Simulink and Simscape, they're both block diagram like models, simulation models. Simulink is more like follows first principles, transfer functions, math. Simscape is more representative of how you would see things in the real world. So first of all, we want to have our Solidwokrs like static suspension sketch with most things defined, like it doesn't have to be strictly defined and you could change it later on, but you still want to have some kind of rough baseline to work with. Your your track width, your wheelbase, your ride height, camber, caster, kingpin, angles, stuff like that. And then you could use Simulink to optimize those. Alright, so you can see we have some top level subsystems here. We have FL, front left, front right, rear left. So front is front of the car, rear is rear of the car. And I say that because left and right are not exactly what you might think. I'm looking at this from the front view a lot. So although from the driver's perspective, this highlight wheel is the front right. I just say it's the front left because I'm looking at the front view a lot. Just keep that in mind. That convention just goes for this whole model. Alright, let's go into the front right system. Looks a little complicated, but if you go in closer, these are... So LACM, for example, is the lower arm chassis mount. This is upper arm chassis mount. Here's a tie rod. SH is shock chassis mount. So this is inboard, if you didn't already, tell. There's a wheel. I made it a little bigger so you could see it better. Let's look at how, from a basic level, how these blocks work. So you have your physical, graphic model of what you eventually see in the simulation. So let's start with an example. Here's your upper A-arm, right? Model just as a simple cylinder. Let's go to the chassis. So chassis, here's a step file for the actual chassis, and then the origin of that chassis is, by our conventions, the center of that tube right there, right? But that's not where you want, this isn't where you want the A-arm to be mounted. So what do you need to do? You need to use rigid transforms to move your coordinate system, right? So that's what I did. So you have your chassis as one part, you have your A-arm as another part, right? And your A-arm coordinate system also by default isn't where you want the mounting point to be. It's going to be oriented somewhere like this. You want it to be somewhere like here, right? Not in the middle. So what do you need to do? You need to move it along the z-axis by half the length to get to that end, right? And then you do the same thing from the chassis origin. So you have chassis, A-arm, and then the mounting location is located somewhere in 3D space. You go from the chassis origin, do a rigid transform to that mounting location. You go from the A-arm origin, you do the same thing to go to that same mounting origin, and then you could place what you would call, in here and in real life, a joint. For example, so in real life, this is more like two spherical joints, right? So one here, but we're modeling just virtual A-arms for the sake of some simplicity. So we could just say along this line, it's a revolute joint, meaning just simple one axis of rotation for its DOF. There you go. That's how you define, joints and where the joints are located with respect to two parts. Let's go to the sensor. Also, with these joints, you could define internal mechanics, which I did here. These are just placeholder values for the spring and damper coefficients. Let's look at these sensors. You're going to be looking at these often. So these aren't where the actual calculations are taking place. These are just shortcuts. So if you look at the source, let's look at the source of the shortcuts. It's in the front left, and these are the calculations. You use a transform sensor, which is different from a transform rigid transform. So transform sensor is just a transform between two frames, right? You have a B and a F, your base and your follower. Whenever you measure something, right, you need something to measure with respect to. In this case, it's a road frame. And then your follower frame, the thing that you're measuring is what? Let's look at that connection. Go out. All right, this is what I was just in. So connection 1, follow this line. Where does it connect to? Connects to, right there, R. So the wheel. Let's go to the wheel origin, right? So that's the wheel origin. It's visualized right there. So you can see the z-axis points out and slightly up. It doesn't point perfectly straight out because of the caster angle, but it doesn't really matter in this case. I already accounted for that, and honestly, I don't think you even need to account for that. But you could, as we can see, if you follow the right hand rule, with your thumb pointing at the axis of rotation, then your camber corresponds to rotation about the z-axis, and your toe angles correspond to rotations about the y-axis. How do you use that information? So go back to here. If you select transform under the rotation menu, then it gives you a 3x3 rotation matrix from which you could calculate the Euler angles, right? Which are just standard angles about the rotations about the axes, x, y, z axes. We need the y and the z, right? So if your rotation matrix looks like these, this is the equations you use. Let's see. Right. You're using two things here. This is a physical signal from the multibody, right? But this is going to a Simulink converter, which you need to do in order to perform this fairly simple math. These are selector blocks to select which elements you're selecting from the 3x3 rotation matrix, and then that goes into a scope so you could visualize it. Same for wheel heights. Let's see where that comes from. Right, here's a transform sensor. Your base is, let's see, the chassis, or a point on the chassis. In this case, specifically the lowest point on the chassis, which is last year was 2 inches below the chassis origin. So I counted for that. Your follower frame is what? Let's see where that goes to. That's the wheel, right? So it goes to the center of the wheel. That's where the R frame is, right? But in order to get to the bottom patch, I just added the tire radius, right? Half the diameter, and you get basically the right clearance, the right height. IC, RC, I just did it for the front here. It's a bit more complicated. Right, so here's how we calculate it. From the front view for a double A-arm suspension, you get the intersections of those upper and lower A-arm lines, right? The lines that they form. And then you get that intersection point. From that intersection point, you drag it along to the contact tire patch. You do that for the other line, and then the resultant lines, their intersection, that's the roll center. So how do we do that? So we need to get each of those 4 lines first, right? In 2D space, right? Since we're just doing a 2D projection, we need 2 points to define each line. So I use a chassis mount point and the knuckle mount point for each of those arms. You can see that here, right? So chassis mount point, the X and Y coordinates going to this and this, right? And then this and this. That creates, you have 4. So these 2 points create a line, these 2 points create a line. I do the same thing for the other side, right, on FR. Where'd it go? Okay, IC calcs, yeah. These 2 points create a line, these 2 points create a line. And then I put that into very simple Matlab script just to find the intersections. I do that for the other side. And then I get the bottom contact point of the tire to the ground. Then I get the lines and do the intersection. And I can visualize it with just a simple sphere. Oh, and for the wheel platforms, so how that works is these rectangular things, they're restricted to just move up and down, and they're in contact with the bottom of the wheels, right? I'll try to make it simpler, but you see these sine wave inputs into these rectangular things, right? So those are in meters, right? How much it goes up and down, but there's an absolute function to it. So from the static position, it only goes up. It doesn't go below the static position because it's an absolute function. It's in meters, so 0.254. I have it corresponding to 10 inches, I think. That should be 10 inches. 10 inches of wheel travel. You could totally change these to make it, let's say you wanted to optimize just for the first 25% of the wheel travel, and you could do that too. If you want to optimize for different ranges of wheel travel, that works. So for optimizing, there's if you look up on here, there's apps. I forgot if I had to get this as an add-on separately or if it came by default, but either way, response optimizer, I have it open, I think. Right. So you define the variables that you want to optimize. Right. You select it. You find the ones that you want to optimize for. I'll do an example for bump steer. Well, I want a specific example. Let's say I'm just selecting some random ones. I say I want to change these. It's best to define the bounds, right? You don't want it to iterate through bounds that don't make sense. Be realistic with the bounds. And then once you define those, you define your goals, basically. So, signal bound. You add a signal. Signal. Where'd it go? Okay, let me delete all these. Alright, you add a signal. This little window comes up. Let's say you wanted to... Let's go back to this. So let's say I put the platform movements or the front platform movements to true. Right, I want the fronts to move so I could see how that changes the toe angle, let's say. I go to camber and toe. Let's say it's symmetrical, so I'll just use the toe for the left. I go on this, select that signal line. It should pop up here. Select it, press OK. And I could... So upper bound or lower bound. You can't do both at once. You need to do one at a time, right? You define the time bound that you want this goal to be applied to, and then you want to do your bounds, right? So this is less than or equal to the bound, so this is a upper bound. Let's say at most I want 1 degree, right? And then I would do this again. Select the same signal and then make it as a lower bound, and let's say I wanted to have a minimum the lower bound to be like 0 toe. And then you just press optimize right here. I'm not going to do it right now because it might mess something up. It goes through the optimization process, and if it can't converge, it hasn't found a solution, but it tries to get as close to it as it can. You could use this to do, bump steer analysis. Let's say I run this and I did that optimization that I just mentioned. And let's say my variables are like where the steering rack is placed and like the tie rod length, steering rack length. I forgot to run this, so let's run it. Oh wait, no, sorry. This is M22. I'm looking at M23. Run that. Update it. It looks broken right now, but it should fix itself. Yeah, there you go. So you can see that steering is also on, as well as the suspension movements. Yeah, so conclusion. It's very powerful. This is a very powerful tool, but it's not like a dedicated tool for suspension systems. So there's no like one button just to, do camber sensor. I had to do those calculations. But the upside to that is that I could add more sensors to whatever, and I could make a lot of changes and customize it. So it's powerful in that sense. Again, downside to that is probably just a steeper learning curve. I'm hoping I could maybe simplify this further so it's easier to use and more accessible. But for now, this is where I'm at. I'll make some updates to it. And if you have any questions, you guys could, feel free to reach out to me and ask. Yeah, that's about it.